Hi, this is your cheat sheet on 2D kinematics. This video is a continuation of my previous one on 1D kinematics. I've linked it in the info card and it's on my channel page, so go watch that before watching this one. We're going to be going over gravity, the relationship between the x and y axis, projectile motion, which includes projectile graphs, the angle of launch, equations, and uneven trajectories. Let's go. So far, we've been talking about just one dimension, the x-axis. But now we're going to take what we learned from 1D kinematics and apply it to our y-axis, newly unlocked. Objects can also have velocity and acceleration in the y direction, just like the x-axis. Now, a special case of acceleration going downwards, the y-axis, is gravity. Gravity is the force that's pulling all objects to the Earth, and it doesn't matter regardless of size and weight. Talk about that a little bit later. Thinking of gravity as acceleration, even though it's a force, really helps to wrap your head around this stuff when you have to calculate projectiles, things like that. Now let's take a heavy object, like a bowling ball, and a light object, like a golf ball, and drop them off a cliff. At the bottom of the cliff, assuming there isn't any air resistance or any other factors affecting the fall, both objects will hit the ground at the same time, regardless of its size. Gravity is constant and will always pull at objects at a value of 9.8 meters per second squared. All objects in free fall will have its velocity increase at this rate. An important note is that velocity and acceleration in the x-axis and y-axis don't affect each other at all. Whatever motion is happening going left and right doesn't affect anything going up and down. To illustrate this idea, let's take an example. Here are two arrows. One is dropped onto the ground to the force of gravity pulling it. Another one is launched with some velocity x, but still has gravity acting upon it. Both arrows start 30 meters above the ground. We'll say the ground level is 0. How long does it take for both arrows to fall? Do you think that the arrow that was launched would take longer to fall to the ground, right? But no, and let's prove it with math. Using one of our equations and plugging in our values with 30 as our initial position, 0 as our initial velocity because it starts at rest, and negative 9.8 as our acceleration. Remember, acceleration is a vector and is always going down, meaning we indicate that with a minus sign. Doing some algebra, simplifying things gives us a final time of around 2.5 seconds for the arrow to touch the ground. Now let's use the same equation for the arrow that wasn't launched. And if we plug in everything and simplify, we also get 2.5 as our time. They both fall at the same rate and hit the ground at the same time. The math proves that regardless of how much velocity the object has in the x direction, all objects will still fall at the same rate of gravity. This is basically the same case as the bowling ball and golf ball, except the x velocity here is really to just throw you off. It's a trick question. The arrow will go farther in the x direction because of that initial velocity as it falls to the ground, but they will still touch the ground at the same time. Now here's the heart of 2D kinematics, projectile motion. In textbook terms, it's when an object with a given initial velocity and angle moves under gravity. Simple terms, it means we're deciphering the motion of any object that's been launched, thrown into the air, etc. The path which the launched object will take will always follow a parabola. The parabolic path here might bring up memories of Algebra 2, or I don't know, you're even taking it right now. The top point of the parabola, the highest the object will ever get, is called the apex. The path before reaching the apex and after reaching the apex are actually symmetrical. Granted, the surface from which the projectile launched from and lands on is at the same elevation. This is what we would call an even trajectory. For the projectile to even move in this path, it needs to have some launching angle pointing upwards. So let's just say Jimmy, he's here, he's back, and he's ready to launch at some initial velocity, vi. and the velocity is pointing some theta degrees off the horizontal. To figure out the path you'll be taking, we'll first need to know the x and y velocities that make up the initial velocity. The y velocity will tell us how high Jimmy will go and how long Jimmy will be in the air. The x velocity will determine how far in the x direction Jimmy goes in the time it takes for him to reach the apex and touch the ground. If you don't see it yet, this makes a right triangle. So finding these velocities is like finding the bases. It's simple trigonometry. You can easily find them by using sine and cosine. This is a projectile graph where we take a look at velocity and how gravity affects it. So this is what's happening to Jimmy as we throw him into the air. Sorry, Jimmy. Velocity starts high, the highest it will ever be. But as gravity is making it go downwards, it ends up rotating. At the apex, it is perfectly parallel to the ground and then falls back down, accelerating. If we were to dissect the velocity of the object into its x and y components, we see something intriguing about Jimmy's velocities. As time goes on, the velocity in the y direction decreases. We signify the magnitude of a velocity with the length of the arrow. So as time goes on, velocity decreases until it meets the apex here, where there's no y velocity. And then it starts pointing downwards and accelerating downwards till it hits the ground. Probably hurt for Jimmy, but that's fine. However, remember, I said that the x velocity doesn't affect the y velocity. Whatever value it has, it'll stay constant for the whole trip. We'll talk about why this happens in our forces unit. But for now, just remember, stays constant. All right, so now I'm going to dump some equations on you to take some notes. To find the time it takes to reach the apex, it's this. From here all the way to here. For an even trajectory, since this part and this part of the parabola are symmetrical, we can just multiply this equation by 2 to get our total time. The highest elevation is given by this equation, and you can find how far it went with this equation. The range is talking about the distance from its initial all the way to its final position in the x direction. The equations shown in the 1D kinematics video can also help in your problem, so keep those in mind too. And these are actually derived from those. So if you don't remember any of these, remembering those 1D kinematic equations really comes in clutch. Now let's get back to our cliff, and Jimmy's here somehow, and he's going to throw a golf ball up in the air, and it's going to fall down, meet its demise. Now when we first looked at parabolas, the starting and ending points were on the same elevation. But here, the starting point is higher than the ending point. In this case, we can't actually use the t total equation from before, along with a few others. So for even trajectories, we saw that since the trajectory on both sides was symmetrical, it was quite easy to calculate the trajectory. However, now that it isn't symmetrical, we have to treat it differently to calculate anything we want. To find anything from the total time, height of the apex, etc., we actually need to calculate the two sides of the parabola differently as its own entity. And the part before the apex, initial velocity, would be right there, going up, moving all the way to the apex. The second part of the parabola, which we'll treat as its own entity, its initial velocity would be going like this and accelerating downwards till it reaches its doom. You can also use this mentality to flip the trajectory based on the problem that you're given. Alright, that's all of 2D kinematics. I only went through everything like pretty fast, so make sure to supplement your learning with practice problems and whatnot to really drive in these concepts. Make sure to like and subscribe, and I'll see you in another video.